Hello and welcome to this lecture of the course Elements of Mechanical Vibrations. In the previous session, we got introduced to the basic philosophy behind modeling a given system as a continuous system, and we also got introduced to the solution process, the modeling and solution process of simple continuous system as stretched string. We got the expressions for the natural frequencies and mode shapes. In today's lecture, we extend that discussion in solving the same system for its free vibration response to initial conditions. Later, we take the case of vibrations of a bar. So, here we shall be discussing the longitudinal or axial vibrations of a continuous system. So, we take an example, and it's an interesting example of finding out the response of a stretched string to initial excitation. So, in this case you can imagine that on a guitar string, which are the strings are fixed to the boards at both ends, right. So, this is like the string is stretched, and you attach it to the bridge on both sides, and this metallic string is now a stretched string. Now, how do we generate sound in the guitar? The player basically pulls the string outwards. So, you are basically stretching the string outwards with a value at initial time W naught x. So, basically the string is stretched like this at initial time. So, the player basically pulls it at any location. So, we assume that as an example here, that the player has pulled the string at its central location by a small distance h. Okay, that is at time t is equal to 0, he stretches that string up and then releases it. Okay, so when you are stretching, you are basically giving some initial displacement for the entire string and then releasing it. When you release it without giving any initial velocity, which is typically the case when we play the guitar, we are not going to push it with certain initial velocity. So, we are simply going to release it. Now, when you do that, you essentially are giving initial displacement conditions, not the initial velocity condition, right. So, if you do that, this is how the initial displacement is going to be. Obviously, for this particular region, the displacement as a continuous function in x, okay, as a continuous function in x, this distance which is being pulled is going to be given by x at time t is equal to 0 will be h x upon L by 2, okay, which will follow the straight line function. Okay, so the displacement at any position x for this region of the string, that is 0 less than equal to x less than L by 2, this is going to be the displacement at any position x that the string is going to get subjected to. Whereas in the remaining part, you can show that the same displacement is going to be h over L minus x. So, that is between L by 2 x up to L, right. So, yeah, you can treat them to be like that. That is how this this function is going to be looking like. That is the initial displacement that you impose on the string at t is equal to 0. So, this is going to be L by 2, and that will make it 2h. So, this is going to be 2h by L minus x. Okay. Now these are all the prescribed initial displacement condition, and because we are simply releasing it at t is equal to 0, the initial velocity condition is obviously going to be 0 at all positions along the length of the string. Now if we substitute this into the expression of Cn and Dn, we know that Dn is going to be 0 because you recall that in the expression of Dn, this appears, the initial velocity appears. So you can see that because W naught dot x is equal to 0, initial velocity being 0, all the Dn's will be 0, and you will have to find out what are the Cn values. So it is quite possible that when you try to integrate the expression for the Cn, it will be in two parts. One, when the x is going to change from 0 to L by 2, and then the second expression, which is this, is going to apply from L by 2 to capital L, obviously. So you have two different integrals to be evaluated, so you can integrate it by parts, and when you integrate it by parts, this is finally the expression for Cn that you will get, which gives you the value of Cn as a function of the initial plucking distance, that is h, and the expression here in sine function, where n will take the value 1, 3, 5 and so on, and is going to be equal to 0 for n equal to 2, 4 and 6. That comes out from the integration. You can work that out yourself to cross check that this is true. Okay, so there is a reason why this happens, and we will discuss that very shortly. So now that Cn has been obtained, our Wx comma t by substituting the Cn value can be written like this. It is going to be obviously a summation, right? So the total Wx comma t was a summation of n equal to 1 to infinity, and it will be sine omega n x by L into Cn cos omega n t, right? So this is basically the expression that by substituting proper values of Cn and cos omega n t, this is how you can get that, because omega n has been replaced with pi ct by L. This also you can find that this is almost the same as cos omega n t. Okay, and of course you have this omega sine omega n x by L. Now let's look at this omega n expression that we had derived. Omega n was derived as n pi c over L, and for the first term n is equal to 1, so it is going to be pi c by L. So cos omega n t for n is equal to 1 becomes cos of pi c by L into t, right? So cos omega n t for n equal to 2 will be same as cos 2, sorry, now because for n equal to 2, 4, 6, this Cn is equal to 0, so we'll have to skip the second term. So I'm going to jump to n equal to 3, and therefore this is going to be 3 pi c by L t, right? So that is going to be the third term. Okay, now so this is cos omega n, and then sine omega nx by L. So sine omega n is again n pi c over L, that is omega n, and sine omega by c into x, I'm sorry, so this is c, and n pi c by L will mean this, and so this basically the mode shape is going to be sine n pi by L, right? Now for n is equal to 1, the first term, this particular term is going to be sine pi by L, pi, this will be x. So I have only replaced omega by c, so it has to have x also here. So sine pi x by L. So this is how the sine pi x by L is the first mode, and this is the harmonic time function cos pi ct by L, pi ct by L. And then the third term, second term is absent. You can see that all the the even terms are 0. So the second term will have sine 3 pi. So n is equal to 1, this is going to be the case. N is equal to 3, you will have this as sine 3 pi x over L, and that is how it is going to be this. But at the same time, you should notice that Cn is not only going to have this particular term, but it is also going to be multiplied by this term, out of which 8h by pi square is common in all terms. So if I take it outside, this is a common multiplying term, and internally it is going to be all these terms. Now here you should look at what this sine n pi by 2 will be. If n is equal to 1, sine n pi by 2 is going to be plus 1, and for all subsequent cases it is going to be minus 1, or for n is equal to 3 is going to be minus, for n is equal to 5 it is going to be plus, and so on. So this is all going to alternate in their signs. In addition, although 8h by pi square has been taken out as a common term, n square remains, and therefore the second term will be 1 by 3 square, which is 9. The third term is going to be 1 by 5 square, which is 25, and so on. Okay, so this is how the entire total response of the stretched string has been obtained. Now you will wonder as to why do you have only the first, third and fifth term, and why not second, fourth and sixth term. Mathematically one can prove and one can show that that is the case, that the value of Cn is 0 for all the even terms in n, whereas all the odd terms in n has a non-zero value of C. Physically it is quite easy and straightforward to validate, right? Why is that so? Why is that happening? That is quite simple to see if we look at the mode shapes in those values of n. Okay, so what is our first mode? We discussed the first mode to be this, right? This is our first mode. What is our second mode? The first mode, second mode was this. And what is the third mode? I told you the third mode would be something like that. And what? So second, and this one is third mode, and the fourth mode would be this. You can notice that each higher mode keeps on adding one more node point, right? So for example, this is the second mode, which had one node, the third mode had two nodes, and the fourth mode had three nodes. Okay, so these are node positions. So there are three nodes in the fourth mode. In the third mode you had two nodes, and in the second mode you have one node. So one node kept on getting added. But what is more important to notice from these mode shapes is that at all times, right, at all times, at all times this particular position of the second mode will have zero displacement, right, which means that when the string vibrates in the second mode, it has to have zero displacement at the center of the string, isn't it? Irrespective of the time, this part of the string will have zero displacement in the second mode of vibration. Okay. In the third mode of vibration, this particular position and this particular position will have zero displacement. And in the fourth mode, this position, that is again at L by 2, the string has to be having zero displacement irrespective of the time at which you are looking at it. So at all times, the central position of the string should be zero displacement, okay, in the second, fourth, and you can show that the same will be in the sixth mode. So which actually means that all the even modes, okay, need the response to be 0 at L by 2. Okay. Now how have you given the initial displacement to the string? With a non-zero displacement at L by 2. Okay. So at L by 2 position, your initial excitation to the system defies or contradicts the corresponding mode shape, second mode, fourth mode, sixth mode, eighth mode, and so on. So it is not in tune with that initial displacement expected for that mode to participate or to get excited. Okay. So that is the physical reason why the Cn is going to be equal to 0 for all the even harmonics or even modes, whereas it is non-zero for all the odd ones, that is n equal to 1, 3, 5 and 7 and so on, right. This is the reason why in this particular case the initial displacement given is such that those modes cannot get excited. Okay. Now it will be left to you as an exercise to find out the corresponding response if I stretch the string initially like this rather than stretching it from the center. Okay. So you can take this to be maybe L by 6 or L by 4, whatever you feel convenient, and then find out, write an appropriate initial displacement expression the way we wrote here. This will get slightly modified based on where exactly are you pulling it up. Okay. And then you will find that Cn and Cn values will change, and then the modes participating will change. Okay. What is also interesting is look at the amplitude of each of the participating modes. Okay. What do I mean by that? Look at all these individual expressions. This is of course the common multiplying factor. So we will look at each of the, this is the first mode, right, its value is 1 here. What is the second mode? So this value is of course going to define, this is going to define how much will be the amplitude as a function of x, entire string, but the maximum value is going to be this value. Okay, it's a sine function, so it will have a unit maximum value, but the multiplying factor, this is basically the amplitude of it, minus 1 by 9. Okay. What is the third mode? So this is second mode and this is your third mode. Sorry, this is your third mode. And what is the amplitude or the contributing factor of the third mode? 1 by 25th of the first one, relative to the first one, right? So the first one being 1 here, the third mode contributes by 1/9 of the amplitude of the first mode. The fifth one contributes 1/25th of the first one. Okay, and so on. So it is quite straightforward to show that all the higher modes are going to contribute lesser and lesser, almost their contribution will be negligible. So if you compare the contribution from several modes, you will find that if the first mode is 1 unit here, okay, the first mode, the second mode is going to be 1/9 of the first, and the third one will be 1/9, the second one is absent, and the fifth one will be almost not seen. And that is because the initial displacement that you have given is such that it it is matching to certain extent the first mode, more or less. It's not exactly half sine wave, but it is reasonably close to the first mode. Okay, you can show how do they relate when you give an initial deflection in a slightly different form. It's all a simple mathematical exercise that you can carry out to explore further into how and what happens to the relationship of different modes when you give the initial displacement slightly different than what you have given here. Okay, so it is because your initial displacement here which you have given is actually matching reasonably close to the first mode shape. Therefore first mode contributes significantly higher and the higher modes do not contribute as much. Okay, and in general it is true that when you give some arbitrary excitation like this, higher mode natural frequency are going to contribute lesser to the total vibratory response, unless you give the initial displacement literally like this, where where the second mode is going to be predominantly contributing to the total response, and in this case of course the first mode will not contribute. Why? Because by doing this kind of an initial displacement, you are forcing the central part of the string to be 0 in its amplitude, whereas the first mode needs to have non-zero displacement at that point, right? So this is how even in 2 degree of freedom system you have seen that if the two masses are initially moved together in one direction in the same amplitude and then released, it will continue to vibrate in the first mode only. If you stretch it in the opposite direction so that the mode shape is 1 minus 1 and then you release it, then the whole motion is going to be only in the second mode, first mode will not contribute. It's quite similar, and so you can see that what you learned in a single degree of freedom system is simply getting extended for such a continuous system also. So if you know things on the single degree of freedom, it's much easier and easily you understand the more complex vibratory systems better. So what happens when you consider a different kind of a musical instrument? You might have seen santur as another musical instrument, a stringed instrument, right? So the player does what? He has the hammer, and those hammers he strikes. He holds the hammer and then strikes on the string. The strings there also are stretched strings, and then you strike the string at appropriate locations, right? So there you are not plucking the string. That means you are not giving initial displacement w naught x. You are actually giving w naught dot x as the initial velocity to the string, right? So these stretched strings, if they are given initial velocity, then all your cn are going to be 0 and dn will be non-zero. Okay, and then basically the location at which you hit it, that will decide which particular mode of vibration are going to get excited. So depending upon what pitch the player wants to generate, he strikes at appropriate location on the stretched strings. That's another way of looking at the response to initial excitation of a stretched string. Now, having discussed the stretched string, let's look at um, vibrations of a bar. Okay, so what we are basically looking at is a bar of any arbitrary section. So the cross section can change as a function of the distance. So here also so the bar is vibrating along the axis, so it's basically the axial vibration or longitudinal vibrations of the bar. Okay, we take an arbitrary location x along the length of this bar. Of course, this bar is going to extend, and then we take a small infinitesimal element dx of this bar, right? So I'm basically showing this element like this. Now under the continuous action of all the forces which are set up in the bar, we find that the bar is under equilibrium under the action of these internal forces which are set up at position x. Okay, the original distance here is dx, as we have taken a small infinitesimally small element here out of the total bar of this continuum, and let this get stretched under the action of these forces. Okay, so the bar is undergoing dynamic motion, and this small element is going to be under the action of the forces P at the distance x and P plus dP at the other face of this small element of length dx. Okay, so here, in contrast to the stretched string case, the vibration is not lateral. Okay, it is along the bar. So if you consider this bar is vibrating along the axis. Okay, so each plane is moving back and forth, and there is a continuous extension and compression that might happen along the length of the bar. Okay, now we define the motion given by u x comma t. Okay, so that is a vibratory motion at each cross section given by u x comma t along the length of the bar as a function of the position x and as a function of time t. Now the way we did it for the string case, here as well we will try to get the governing equation of motion by looking at the dynamic equilibrium of this particular elemental a small element of that bar. What will be the net force which is going to act in the direction of the acceleration? So the displacement is assumed here, and the acceleration u double dot is going to be in the same direction, right? This bar can be subjected to external forces f of x comma t, just like the case we did for the string vibration also. So there is an external force, some kind of a pulling force which is going to act, a dynamic force f of x comma t. So now if you if you see the total mass of this element, it is going to be rho of x. It's a density at a position x. The cross section A of the bar is A, that also may vary with x distance. So therefore I can write the cross sectional area A at position x. Okay. So this is going to be the mass of this small element, rho x ax dx. Now rho x typically will not be a function of x for a rod of a same material, right? So rho x may not be a variable, it will be a constant quantity, right? So rho is going to be constant, but as a general case I am writing this as rho of x. What is mass times the acceleration dou to u by dou t square? U is a function of x and t both. Okay, so this is equal to all the forces that act on it. So it is going to be P plus dP, that is the force which is set up here, minus P plus f of x, sorry, f of x comma t dx. Okay. Now what will this be? dP is an incremental change in the internal force, which is, across a very small distance dx, we can expand this P and therefore can write dP as dou P by dou x into dx. Okay, right? So higher orders are all neglected here. So the second order series terms are all neglected, and P cancels out, and then we are left with this particular expression, f of x comma t dx. And I will write this as rho, and maybe I can retain this as it is, dou to u by dou t square dx. Okay, and now rho x ax now, if we also make an assumption that this bar vibrates with small amplitude, this has been our underlying assumption all the time, right? So if the deflections in the bar during its vibratory motion is going to be small enough, we can definitely use the expression E times the strain in the bar element, that is small elemental strip that you have used. This will still apply there, right? What is the stress? That stress is going to be P over Ax, right? P at position x, right, and is equal to Ex, the Young's modulus, times the strain. How much is going to be the strain in this element? Okay, so this, if the deformation here is going to be u x comma t, the deformation on the other face is going to be u plus du, right? On this face, the deflection or the deformation on this face is going to be u x comma t. The deformation on the other face could be slightly different, a slight change in the value. That slight incremental change is going to be du. So how much is the net stretch in the element of length dx, right? How much will be how much is going to be this strain? That's going to be du, which is going to be what? So du over dx, right? What is du? Right? And so that is your du by dx is going to be your dou u by dou x. That is going to be your strain. So I can write this P as equal to ax into ex if E is supposed to if E is assumed to be varying. Of course it is not going to be. The material properties are typically in general constant for that bar, so we will drop that x argument for both rho as well as E later, but epsilon is now going to be dou u by dou x, right? Now I would use this expression into this expression, and dropping x from the rho term, I have rho ax dou to u by dou t square equal to dou x of what? P. P is ax. I can still retain a as a function of x because the bar is assumed arbitrary. Its property, cross sectional property, can change along the length. So ax, but maybe I can drop E as a function of x and keep it as constant, then dou u by dou x as it is here, and of course plus f of x comma t. Now this is basically our governing equation of motion for a bar undergoing longitudinal vibrations. Now here there is no discretization that I have done. There is no lumping of the mass properties or any other properties done. It is continuous system now. Okay, and this is the exact equation, of course, provided it follows the Hooke's law, and therefore this equation has been used, and the material is homogeneous, and then I have used only the cross sectional properties varying along the length of the bar. Now as we do, if we want to investigate the free vibration response, we will drop out again the external forcing term here. Okay, so if I drop the external forcing term and assume that the properties like area and the Young's modulus are not dependent on the x variable, so we are now looking at a simplifying geometry of the bar, that it is constant cross section bar throughout. If that is the case, then I can write this as rho a dou to u by dou t square equal to a into E. If a is continuously changing, then I cannot take a out. Okay, and then the equation becomes little complex in the sense that we will have to have a different method of solution there, and then this is going to be dou to u by dou x square. That basically is our equation, provided there is no external excitation acting on the bar, which I can bring it in much more friendlier form, if I may say so, as 1 upon c square dou to u by dou t square, where now c is going to be square root of rho by E by rho, yeah, Young's modulus E divided by the density. Okay, the density here is kg per cubic meter, so mass volume density, and E is in the units Newton per square meter. So you can find out the speed of wave by using this expression. Okay, so based on this expression the value of C gets determined for a given material. And again, as we have done for the string stretched string case, I can again dou 2u by dou x square equal to 1 by c square dou 2u by dou t square, and then I can write this u x comma t again as two separate functions. One is in x and one is in time. Okay, and I can get the same expressions. Now that this equation is quite same as the expression for the string case, you will find that you will not repeat the whole process. We can definitely show that this is going to be a cos omega by c x plus b sine omega by c x, and then the time function is going to be c cos omega n t plus d sine omega n t. That's the second part of the total solution. Now we will very quickly take the example of a bar which is fixed at one end and free at the other end. So it's, you can treat this to be a cantilevered, not cantilevered but a fixed free bar, quite similar to your a blade which is vibrating along the longitudinal direction. Generally, of course, it vibrates laterally, but as a case we can treat this to be a bar which is fixed at one end and free at the other end. And then, because we know that to obtain the frequency equation we have to substitute for the boundary conditions. You have to get the frequency equation, you have to use boundary conditions. Now what kind of boundary conditions will there be? So x equal to 0 here and x equal to L here. What is the boundary condition at x equal to 0? U 0 comma t is 0 at all times. The response of the bar or the stretch in the bar, the longitudinal vibratory motion at x equal to 0 is 0 at all times, right? That's your boundary condition. At x equal to L, can we say u at L comma t is equal to 0 the way we did it for the string case? We can't, because the bar at the other extreme end, that is rightmost end, is free as such. It is not fixed, so there is no restraint on its motion, okay, vibratory motion. So the bar may have a large vibratory motion at x equal to L, in fact, right? So you cannot say that the u is equal to 0, but we all know that at the free end the forces are 0, right, which actually means that the value of P is equal to 0. At the free end there is no external loading, there is no force acting at the extreme end, which actually means from this equation, that A E dou u by dou x at x equal to L is 0. Isn't it? P is equal to 0 actually means that A dou u by dou x at x equal to L is equal to 0, which of course means that the gradient of the vibratory displacement along x with x is equal to 0. Okay, so what can I do? I use this equation to get the expression for dou u by dou x, which is equal to what? It is going to be A omega by c sine omega by c x plus b omega by c cos omega by c x, and the harmonic time function which I am not writing here, which is going to be c cos omega n t plus d sine omega n t. So those are going to be there. So this dou u by dou x at x equal to L will be what? This is going to be minus a omega by c sine omega by C L plus B omega by C cos omega by C L, and this harmonic time function is equal to 0. Okay. Now, what is the first substitution of the first boundary condition? We know that x at 0 is going to be 0, which is what is going to give me what, a plus b is 0. So a into the harmonic time function, which is c cos omega nt plus d sine omega nt is equal to 0, which actually means that at all times a has to be 0, isn't it? That is quite similar to our straight string case. Now if I substitute for a is equal to 0 in this equation, what do I get? B omega by c cos omega by c L, this times the harmonic time function bracketed quantity equal to 0. Now for all times this quantity cannot be 0, so obviously this quantity has to be 0. Now b cannot be 0 for non-trivial solution, we discussed that earlier. So the only thing that happens or valid here is omega by c into L has to be equal to 0. That's the only equation that we have. Now what does this mean? Omega by c L will be equal to right, which actually means that the natural frequency omega n for the bar is going to be pi c by 2L 2n minus 1. That's the frequency equation for you. Actual frequency equation is this. This is basically the expression for the nth mode natural frequency. Okay, you substitute for n equal to 1, 2 and so on up to infinity, you will get all the natural frequencies. Clear? So what is the first natural frequency? Second one, and so on, right? What is the mode shape? Mode shape is still the same. Now I will rub this out to make space for showing what the mode shape is going to be like. Is that clear? So omega 1, omega 2 have been obtained. Now we are looking for how do I get the mode shapes now, right? So let's look at how we get the mode shape. So u x comma t is still going to be, see, a has been shown to be 0 and b is non-zero, so you basically get sine omega, so un, so nth mode response is going to be sine omega n by c into x. That is basically the mode shape because b is not 0, and then of course you have cn cos omega nt plus dn sine omega nt. Please make a note that this is very similar to our stretched string case, right? So you still have this as your mode shape value. Now look at what are we getting here as the first mode. Sine omega n omega n by c is going to be pi by 2L. See, omega n by c, from this expression I can write this as pi by 2L 2n minus 1 x. This is our mode shape. So at x equal to 0, obviously what the first mode shape, suppose what is the value of the displacement? It's going to be 0. Sine this particular term at x equal to 0 is equal to 0. What happens at x equal to L? It's going to be equal to 1. So this expression at x equal to 0, sorry, at x equal to L is equal to 1. Okay, but how much for the first mode? So we are looking at first mode shape, right? So sine pi by 2 x equal to L, so this 2n minus 1 is actually equal to 1. So sine pi by 2 is actually 1, and therefore the value of the response, or the longitudinal displacement at x equal to L is equal to 1 unit, right? But that is, so from pi by 2, 0 to pi by 2, there will be no 0 value, right? Sine function changes from 0 argument to pi by 2 argument, from 0 to 1, right? So the response or the stretch in the bar is going to follow this kind of a mode shape, right? So what will happen as the bar moves or vibrates along the longitudinal direction? Although I have shown the motion or the displacement of each of these elements in this direction, actually the vibration is not lateral. It's just the way of showing it that at this point, this particular element is going to be moving or stretching along the longitudinal direction by a value equal to this, in relation to a unit value at the free end. That's what the mode shape is all about, right? You show the relative displacements of each of the element of the vibratory system with respect to some reference value or reference displacement of one of the reference element in the vibratory system. So that's basically the first mode shape. Let's look at the second mode shape. X equal to 0 and x equal to L for n equal to 2. Yeah. So how much will that be? At x equal to 0, it's the same irrespective of the n. Yeah. So this is still going to be 0. For n equal to 2, sine pi by 2 x equal to L, this is going to be 3. Okay, which means the value at the free end is going to be minus 1, 3 pi by 2, right? So this is 1 unit, minus 1 unit to be precise. So this sine 3 pi by 2 for x equal to L is going to be the displacement. Now 3 pi by 2 means at 0 position, that is at x equal to 0. So the argument of the sine function for x equal to 0 is 0, and at x equal to L it goes to 3 pi by 2, which means that it has to go through another maximum plus value and also has to go through a 0 value at pi, right? So you can show easily that at x equal to L by 3, this sine function will be what? Pi by 2 L, and because n is equal to 2 here, this is going to be 3, and L by 3 is all going to give you what? 1 value, sine pi by 2. Okay, so x is replaced by L by 3, and n because we are talking about the second mode, so n is equal to still 2, right? So this function, the mode shape, will take a value of plus 1 at L by 3 position. So if you divide this into 3 equal parts, this is my L by 3. At L by 3, the value of this sine function is going to be 1, right? And similarly you can show that at x equal to 2l by 3, this sine function pi by 2 l 3 and 2l by 3 turns out to be 0. And so this mode shape is going to pass through a nodal position here at 2l by 3 position, and at l by 3 it will have plus 1. So what is going to happen, that the bar is going to have maximum axial deformation at this point while vibrating in the second mode, and will have a zero displacement or a zero deflection at 2l by 3 position, and will have maximum deflection again at its free end, but the deflection here and deflection here are going to be in the opposite sense, okay, which means at one end there will be compression, the other end there will be stretch. This is how the second mode shape is going to look like. So this is its second mode shape. Now what is the relevance of these? Knowing the mode shapes in general, I am saying that if I know that this bar is going to vibrate close to the second mode, okay, if this bar is going to vibrate close to its second mode because of the operating conditions, then any mounting on this bar would be preferred to get located here. Why? Because that location of the bar will see no vibratory motion or significant vibratory motion. If I want to clamp anything there, I would have a preferred location to clamp at the node position, because at all other position there would be stretching and compression and continuous vibratory motion taking place. Okay, so the positions of the nodes or nodal line in a two-dimensional vibratory structure, the position of these nodal lines or node positions is important from these practical viewpoint, that I would like to locate if there are any other additional mountings there. Of course, any mounting will change the vibration characteristic of that structure, but still if that mounting is not going to substantially change the vibratory characteristic in terms of mass and stiffness, then it is I would use that node position location to find a more favorable position of these mountings. So if I want to put some kind of an sensor or an instrument which should see less amount of vibratory motion, then those are the preferred locations that I can use. Okay. And of course, the rest of the process of finding out the free vibration response to initial conditions is exactly same as that of the string. So that part is going to be left to you to extend exactly the way we discussed it in terms of in the case of stretched string. So nothing changes, it's the whole process still remains the same, but these are small differences that are there in terms of vibrations of a continuous bar. So the bar here is not again discretized into lumped elements, but it is treated as a continuous distribution of the mass property, and the cross-sectional dimensions are also continuously changing, and so we got the response as a continuous function in x and time. So that's how the response has been obtained. So the summary of this lecture, we understood how free vibration response of a stretched string to some initial conditions can be obtained, what is the basic process of doing that, and we also then got introduced to the longitudinal vibrations of a continua like a bar, and understood how the natural frequencies and mode shapes of a bar can be obtained. These are a couple of review questions for you based on today's discussion. These are the answers.